Hello, everyone. Welcome to our last lab of physics 4A. For this lab, we're going to measure the speed of sound with the apparatus you're seeing right in front of you. Right here, connected to this dowel rod is a microphone. The microphone is going into one of these tubes. Let me show you a tube for a moment. That's what the tube is looking like, but we're just setting it up so that sound travels down that tube and reflects. The idea is very similar to snapping your fingers or clapping your hand right next to one of those big buildings in downtown LA, or right next to like a mountain in Mount Baldy or somewhere like there, where you go and you clap your hand and a moment later you hear the echo. So this is an echo experiment. The experiment goes the following way. I'm standing right next to here, whereas my partner, in this case myself, is going to start the experiment in a computer behind you. It's kind of pre-programmed in such a way that the moment the computer gets any signal, it starts recording, because the recording is very, very swift, very quick. After all, if you're thinking about it, if this was 1.5 meters and 1.5 meters back, that means 3 meters. The whole 3 meters back and forth would take about 100th of a second for the signal, first of all, to be recorded, then to come to the bottom and echo back 100th of a second later. That's why it has to be automated. Well, let's make a little experiment here. And I will just go ahead and do snapshot. I'm going to the computer, starting, snapshot, and there is the echo. Now it's far away from you, but don't worry, I'm gonna go and do this experiment in a moment and go and get very close so that you can see the actual details. And what I'm doing right now is I'm just measuring the distance to the building, if you may, from the place where the fingers were snapped, which is right at the microphone, to the floor and back. Now, what you can see here are 2 meter sticks, so that I'm not cheating you of anything. You can see that this distance right here is about 1 meter and 30 centimeters, but I'm going to be as precise as I possibly can. It's 1.314. So this is the first number that you are recording in the experiment, 1.314. Now I'm going to take the webcam, get it close to the computer so they can see what the file would look like that you will be analyzing here. So of course, I'm going to post on Canvas a file of this sort, where when the snap just started, it was right there. And the first significant peak happened right there. And so you can go from, again, let's go from right there to right there. And the number, hard to see, but I can tell you it's 0.0076197. Don't try and remember those numbers. You need to do them yourselves. The big problem in this experiment is to try and see what is a good echo. Like a trough versus a trough. And the very first trough is at the very beginning right here. And the very first troughing is about right there. And that looks to be, again, 0.0075174. You should do about 2 or 3 per image, and I'll be sending you 5 images. So, for example, this is first image, so I'm doing save as, and I'm not calling it, I'm gonna be calling it sound 1. Making sure that I'm gonna find it out. I'll put it in downloads. And I'll spell sound correctly. And there you go. You have the first picture for this experiment. Now I'm going to go. So remember, for this experiment, you will have 5 pictures. In each picture, you will take 3 data points. And that's what you're going to average out in order to find the average and standard deviation on the proper times for finding the speed of sound. Now, I'm going to give you a little bit of the theory. So let us continue with the theory. We have our tube, our microphone, and we know that this distance right here from the microphone all the way to the bottom, we know what this distance is. We're gonna call it uppercase L. It was like 1.314, something like that, okay? But we know that the disturbance, the wave, if you made a dense, slightly denser wave, will move like that, hit the back, come back, and come back here. And the way there and back will take it a certain amount of time. My delta t, 1, for example, we said was 0.00754 seconds. I need to find the speed of sound. The speed of sound goes as follows. The speed of sound is equal to 331.5 meter per second plus 0.607 temperature in degrees Celsius. I measure the temperature in this room. I'll do it 0.607 times T, where T is in degrees Celsius. The temperature in the room was measured to be 21 degrees Celsius. You can substitute the 21 into here and find out what the speed of sound is. It's roughly 344, 346, somewhere around this range. But that is your hypothesis. Let's assume that the temperature is incredibly precise, so that the speed of sound hypothesized is incredibly precise. What's a little less precise will be what we actually measure. What we actually measure is that the speed of sound, which we designate as C sub S, is distance over time. And that's going to be, in our case, twice L, right? Because it goes there and back, divided by the average T. Notice that, as usual in physics 4a, the big bucks are being made by analyzing the data. There'll be delta T1 all the way to delta T, somewhere between 10 and 15. I'll just call it N, from which we'll find T average. That's easy. You will also find the standard deviation. That's easy. But there's also an uncertainty of about 2 millimeters in the length L. Or if you go back and forth, that makes it almost 4 millimeters. So 2L would be equal, we said this was 1.3 14 times 2, but we said plus minus 0.004 millimeters. That's my delta L. Now that starts to ring a bell because it kind of reminds you of that kind of crazy propagation of error we needed to do for the pendulum and for the springs. So that part I'm not going to do for you. But this is the part that you need to remember, that delta CS is a result of propagation of errors. So the uncertainty is a result of the possible two errors, the error in the length and the error in the time. You propagate those errors and you get the final uncertainty in the speed of sound. Then of course at the end you'll get your speed of sound. For example, if I did this 1.314 times 2 divided by 0.004, divided by 0.007, and I'm just looking at what I have right here. I have 0.00747. And as we speak, I'm doing the calculation. And the number that I get is 374. Just a second, that's wrong. I punched in the wrong number, sorry. I got 351.8 meters per second, which is a little bit too much, okay? But that's what I got. Remember, I have like 10 or 15 of those measurements. I'll have an average and standard deviation, and that's what you're supposed to be doing. Okay, by the time the class starts, you'll have 5 files, and these will be logger profiles, and that would be what you will need in order to finish this lab. Good luck.